turbo engine running.
Absolute genius.
Get this.
Welcome.
This is the show where we bring you
Science.
What that essentially means is
discoveries,
Advances.
Questions. Research.
technology.
Unbelievable.
Without further ado,
This is The Naked Scientists. Hello, welcome to The Naked Scientists. This is the show where we bring you the latest breakthroughs in science, technology and medicine. I'm Chris Smith. Coming up, the UK detects its first case of the new Mpox variant. Some are saying what took us so long. Also, the discovery of a lost city beneath the jungle canopy in Mexico. What is it and how was it discovered? And the robots helping Cambridge scientists understand the evolution of fish.
From Cambridge University's Institute of Continuing Education, this is The Naked Scientists.
First this week, a case of Mpox caused by an outbreak of the Monkeypox virus variant in Central Africa has now been detected in the UK. The World Health Organization declared Mpox a global health emergency back in the summer. We produced a special programme on the virus at the time, and one of our contributors was Michael Marks, who's Professor of Medicine at the London School of Hygiene and Tropical Medicine. I asked him to bring us up to speed on what's been happening.
There are sort of two families of this virus, one that circulates in West Africa and one that circulates in Central Africa. And this is a virus that normally lives in animals. Actually, it doesn't live in monkeys, despite the name. It probably lives in rodents. And from time to time, the virus goes from being in animals to getting into the human population. And in humans, it causes an illness where you may have fever and headache and muscle pains, and most classically, people will develop a rash on one part or many parts of the body.
And what do we know about the case that has been reported in the UK just now?
We know that, as I mentioned, there are these sort of two families of the virus, and clade 1, which is normally thought to be the more severe virus, is predominantly spreads in Central Africa. So although we've had many cases of Mpox in the UK before, those have all been clade 2 virus. And what's now been described is a case of clade 1, in fact, clade 1b, which is the first time this clade has been reported in the UK. We don't have very many details. Obviously, we need to protect the confidentiality of the individual involved, but we understand that they have returned from Africa, from a part of the world where there is a lot of transmission at the moment of this clade 1 virus. And we have seen similar episodes in a number of other countries around the world, for example, Sweden. In relation to this large outbreak in Africa, what we're seeing is small numbers of cases then being imported to other countries around the world.
And based on what we are seeing in humans who are part of this outbreak, we can anticipate probably our case will have similar sorts of symptoms. What would they likely be?
Illness is normally characterized by what we call a prodrome, or that's a sort of illness that arises before the main symptoms. So the prodrome is a bit like having flu. So you might have fever, sore throat, headache, and muscle aches. And then individuals will develop a rash. And that rash can be localized to the part of the body where you came into contact with the virus, or the virus can spread around the body through the blood and other parts. And the rash can then be all over the body. Most individuals have a relatively mild and self-limiting illness from which they make a complete recovery. A small subset of individuals may develop more severe disease, where the rash can be very extensive with hundreds of lesions all over the body.
How should they be managed, these cases then? And I don't just mean the individual, because this is an infectious disease, so presumably a component of the management must also be consideration of who else they may have given it to or got it from.
That's correct. So if we think about the individual, at the moment we don't have any specific drugs to treat Mpox. There are a number of drugs that are in studies, but there are none that we know for certain work. So management of the individual is really what we call supportive care. So that's analgesia, treating any additional infections, making sure that they're not dehydrated, making sure that they're generally looked after. And then there are the public health interventions, and they can broadly be thought of in two sections. So there's isolation of the case so that they don't lead to further transmission. and tracing of that individual's contacts, so people that individual has had close contact with who might be at risk, so that they can be monitored, and if they do develop symptoms, they can be picked up very early. So that's sort of reducing the risk of onward transmission and follow-up of the contacts. And then the second strategy is vaccination. So there are vaccines that are effective, and for example, they can either be given to contacts after they've had exposure of a case. We call that post-exposure vaccination. It's effective, but it's not the best strategy. And it's more effective to give vaccine in advance to groups of the population who we know are at the highest risk. So that's pre-exposure vaccination. In the UK, the previous outbreaks of Mpox have been very strongly amongst gay, bisexual men who have sex with men, and therefore they are the group who have been predominantly offered pre-exposure vaccination.
How will the staff who look after this person, while they're presumably highly infectious because they're at the peak of their symptoms, how will they be kept safe?
So again, there are sort of two broad strategies. The patient is being managed by a specialist infectious diseases unit with a lot of expertise in this particular disease and similar diseases. So there are what we call universal precautions. So as I mentioned, most transmission is really thought to occur by direct contact with the rash. So that can be managed through use of gloves and other protective equipment and sensible interactions with the patient. You don't, we think, catch Mpox simply from, being stood in the same room 5 meters away from someone. So the basic universal precautions that we can take. And then secondly, as I mentioned, there is vaccination available. And because of the 2022 outbreak of Mpox in the UK, many specialist healthcare workers, those individuals working in infectious diseases units, have been offered vaccination. So there, again, we have two strategies: broad principles of infection control, and then vaccination for staff managing these patients.
And what do you feel the threat is, if any, for the wider public in countries in the West, like the UK, like Sweden?
I think that the risk is relatively low, very low, in fact. You'll have seen that there was a lot of publicity when there was a case in Sweden, but there hasn't been subsequent publicity saying, well, there's now a large outbreak in Sweden. And the same is in fact true for most of the other countries where clade 1b has been exported outside of Africa.
Michael Marks there from the London School of Hygiene and Tropical Medicine. Antimicrobial resistance is a natural process that occurs when microorganisms that cause disease become resistant to antibiotic drugs. It's a growing problem, one which former England Chief Medical Officer Dame Sally Davies described as posing a bigger threat than terrorism. One microbe in particular that's proving extremely troublesome, although you may well not have heard of it, is called Acinetobacter baumannii. And it isn't just resistant to one drug, it's effectively resistant to everything we have, to the extent that patients need special isolation precautions in hospital to prevent them passing it on to anyone else. The mortality rate is up to 50%. But necessity being the mother of invention, two teams have been working recently on a solution. One, based in Hungary, and whom we'll hear from in just a minute, is looking at the century-old approach of using bacteriophages, those are viruses that attack bacteria. But first, closer to home, Steve Baker at the University of Cambridge has developed a way to mass-produce antibodies which can neutralise and prevent infection with the agent, the danger posed by which he's absolutely emphatic about.
It's a problem that we hear a lot about, but it's really difficult to emphasise how important it is. There's a real chance that all the antibiotics that we have come to use and rely on are no longer going to be effective. So therefore, we're desperate really for new solutions. The reason that we don't have any, or there's nothing that's forthcoming at the moment, is because it's been largely neglected for other things in recent years because pharmaceutical companies are less interested in it. And also we've really gone through the whole kind of spectrum of different drugs we think that can kill bacteria, and therefore we really need new kind of alternative solutions.
What's been your approach instead?
So what we've done then is think about how we can do things in a slightly different way and work out whether we can kill microorganisms with a different approach. So rather than using small molecules such as antibiotics, we have worked on an approach to try and develop antibodies. So these are naturally occurring, but we can manufacture them to target specific components of the out of a bacteria to try and trigger the immune system to try and do something to kill the bacteria instead.
We've got sort of form in this area, haven't we? Because over COVID, for example, when you and I saw each other quite a bit, we were making antibodies that would attack the coronavirus and do, I presume, something quite similar.
Right, so this is then the reason we really wanted to try it, because this approach, so monoclonal antibodies, has been used for a whole host of different things, including cancer, but also is becoming more accepted for infectious diseases and particularly against viruses. However, it hasn't really been developed or scaled against bacteria, so we're one of the first kind of groups to try and do this and see whether we can identify things that we can hit with antibody on the outside of the bug.
Which bacteria have you gone after then?
The bacteria we were interested in is a bacterium called Acinetobacter baumannii, and it causes really aggressive respiratory tract and bloodstream infections, and particularly people that are hospitalized. And the reason it's so important is because certainly in many countries in Asia and also increasingly in Europe and the US, it is now untreatable with every antibiotic that's currently available. So if you're infected with one of these and you don't trigger a natural immune response to recover, then there's a good chance you'll die from it. So therefore we saw this as a challenge to see, okay, this is a high bar, but can we use this technology to try and come up with something that's a bit different?
And just to add to that, we do see cases in countries like our own when people come back from having been overseas. They bring it back with them, don't they?
Yeah, right. And that's the case for most drug-resistant bacteria. So I think there's a bit of this is a problem of other countries, particularly kind of poorer countries, but like coronavirus, bacteria can travel internationally. They don't need passports, and therefore they can end up in hospital and healthcare systems anywhere in the world. So this is a problem, everywhere.
So how have you got round this? What have you gone for on these Acineta bugs, these problem bacteria? And how have you coupled it to what the immune system then does?
Yeah, so our approach was working with a colleague of mine. They had this chimeric mice that allowed us to immunize the animal, and the animal then generated a large immune response to whatever we gave it. So rather than assuming we knew what to target, we gave the mouse a cocktail of different components of the bacterial cell and let the immune system decide which one was the most important things we thought we could target.
Once the immune system starts making a response, how do you then get the bit of the immune system that knows how to make that antibody that you want? How do you get that out of the mouse and then turn it into something useful?
So this is the clever bit, because then there's a whole process to do this. So we could mine the cells. They're called B cells. These are cells that produce antibody. And these mice have a human B cell repertoire, which means they produce human antibody. So there's a mechanism for us to sort those cells. We collect them, and then we go through a process of screening each individual cell that we can harvest to try and work out what they're producing an antibody against. So it's a lot of kind of grunt work to really find the matching combination of which antibody and how and where it's sticking to the bacteria.
That gives you a cell that has the genetic know-how for making an antibody. So you can harness that. So you can now make these antibodies at scale. How are they used?
So what we did in this experiment, we used it prophylactically. So we used it like a vaccine. The test that we developed was one where we gave these to mice and then let them develop a short-term response within 24 hours later, and then we challenged them with the bacteria. And the idea would be, if we were going to use it in people, we'd either inject it prophylactically or we'd give it intranasally, and then hopefully those people that were vulnerable going into such places where these organisms circulated would then have some degree of instant immunity. The idea long-term probably would develop them more into therapeutics, when if people had these infections, then we could then target the bacteria in the same way and actually specifically choose the immune system to kill those bacteria.
And have you sussed out how these antibodies are achieving the therapeutic effect on the bacteria when they're there?
Yeah, so we think that the antibodies stick to the outside of the bacteria and they label it, and then they activate certain cell types, and that means they get eaten by these macrophages and then they get destroyed. And we think that's a mechanism that these antibodies are performing by, and we think that's why we can demonstrate they protect the mice we infect with the bacteria.
Very encouraging news. That was Steve Baker from the University of Cambridge. We're now back to that team I mentioned in Hungary, who are also trying to solve this same problem, but their approach is a bit different. They've first analysed thousands of samples of the Acinetobacter bacteria from around the world to build a map of which subgroups of the bugs tend to circulate where and for how long. And this they use to inform how to assemble suites of bacteriophages, viruses that can selectively kill bacteria, which are specific for the strains of Acinetobacter which are active in any given geography. Here's the Biological Research Centre's Balint Kinchesh.
So one of the most promising alternatives of antibiotics is phage therapy. Phages are viruses. They are completely harmless to humans, but can kill bacteria, even the most antibiotic-resistant superbugs. So they are very promising alternatives for treatment. However, they also have some drawbacks. The biggest problem with bacteriophage is that they are very specific. So bacteria change over time, and therefore in nature, hundreds of different types exist, and each require different phages. In other words, each patient requires a different bacteriophage. So we asked the question, if this bacterium spreads within hospitals, how does it come that each patient requires a different bacteriophage? Wouldn't it be possible to tell in advance which bacterium or which version of the Acinetobacter baumannii is going to cause the next infection if it spreads primarily within the hospital?
And how are you trying to do that?
To that end, we use genomic surveillance. So we saw that it works brilliantly to track the COVID pandemic, and we thought, okay, why don't we use it for bacterial pathogen, Acinetobacter baumannii, to track the different versions and have phage therapy?
Is the approach then that when you suspect a person has this, you'd collect samples from them, do genetic analysis on the infection to work out where it sits in the family tree of this particular group of bacteria, and therefore what phage might be best able to manage it? Is that the kind of direction of travel with this?
Exactly. So we generated a detailed map of this bacterium. We basically put the different variants onto the map and asked the questions: what's the diversity of this bacterium in a given geographic region, like Western Europe or Southern Europe? And we found that even though this bacterium exists globally in hundreds of types, in a given geographic region, their number is limited. On average, we found that 17 versions of this bacterium exists in a given geographic region, like Western Europe, which doesn't seem to be a lot. It means that maybe a handful of phages could be enough to target the majority of the infections in a given world region.
Do we not have to be careful though, because in this day and age, the world population is more mobile than it's ever been. And so we've got people turning up in different countries from the opposite side of the world on a regular basis, and they could be bringing these things, and therefore their particular type from their world region could be coming to a hospital near you anytime soon, and therefore it might inject additional genetic diversity and forms that won't respond to the phages that you had planned to use.
Yes, that's correct. Therefore, we need to monitor this bacterium, or actually all bacterium, continuously to be able to see how fast they transmitted from one part of the world to the other. And we found that on average, it takes 6 years for a given country to change completely the Acinetobacter baumannii types. In other words, it means that there is a 6-year time window for phages to target the Acinetobacter baumannii types of a given country.
Do we have the right cocktails of phages for this, though, ready to go?
They are definitely not ready for therapeutic application, at least not in our region, because currently in our region, the legal framework is not ready for phage therapy. But there could be other countries where our phages can immediately be used. So right now I'm looking for partners. This is something that it is very easy to do with our map. By mapping this bacterium, I can easily pinpoint to the countries where the same types of this bacterium causes the problem. So I can directly contact basically clinicians and scientists who work in these countries and ask if they need our phages to treat patients.
Balint Kincsés there from Hunran, the Biological Research Centre in Hungary.
The Naked Scientists podcast is produced in association with Spitfire, cost-effective voice, internet and IP engineering services for UK businesses. Find out how Spitfire can empower your company at spitfire.co.uk.
Music in the programme is sponsored by Epidemic Sound, perfect music for audio and video productions.
This is the Naked Scientists podcast with me, Chris Smith. Still to come, how robots might help us to gain a better understanding of the evolution of fish. Before that, though, a PhD student called Luke Thomas has discovered an impressive lost Mayan city concealed under a jungle canopy in Mexico. The find, dating back over 1,000 years, includes pyramids, houses, sports fields and amphitheatres. Elizabeth Graham, Emeritus Professor of Mesoamerican Archaeology at UCL, told me how Luke and his colleagues did it.
He was looking at what are called LiDAR images, and LiDAR refers to a way in which laser beams can be shot at the surface of the Earth, and they reflect the topography like hills and valleys and even caves, and that information can then be turned into a map. But the great thing about LiDAR is that it ignores the vegetation, the jungle. So it doesn't give you images of the vegetation, it just gives you images of the ground surface. And this is fantastic for people like us who work in what people here call the jungle. On the ground, you can walk right past some really large structures sometimes because you can't see them, because of the thickness of the vegetation. So you can see how much of an advantage something like LiDAR imagery is, because it kind of gives us a map of the surface of the land. And in this case, it shows where people have lived thousands of years ago through the ruined buildings that are left behind.
I gather that the study that produced the initial images was of a totally different kind. It was an environmental study that had nothing to do with archaeology, and it was only fortuitous that the author got hold of the LiDAR data and then subjected it to his own analysis.
Yes, because most of the LiDAR imagery up to now has been initiated by archaeologists who raised the funding to have LiDAR imagery of their particular site and the immediately surrounding area. But in this case, Luke had found images that were made in Mexico for an environmental survey. And he thought he would take a look. I'll just, see if through their survey we can recognize any structures. And so they took 3 blocks of areas, and lo and behold, the LiDAR imagery showed structures just about everywhere. They varied in density. I think one block, the density would have indicated rural structures, but the other 2 were really dense, the remains of houses and buildings that were quite dense. And one of them even had the remains of a city, which they called Valeriana.
Did they recognise the significance of what was coming up in these pictures as soon as they saw it? Or did they initially dismiss this as some other explanation?
Oh, no, because by this time, most archaeologists are familiar with the kind of imagery that LiDAR produces. You would have noticed quite well the buildings organized around patios and plazas and things like that, that don't occur naturally. So it was quite recognizable to the researchers that these were the remains of habitations from long ago.
It's almost like a Tutankhamun moment, isn't it, for the discoverers, this?
Yeah, it's pretty exciting, not just because there's been a new major city, but also that we have this much in the way of settlement. And I suppose a lot of my colleagues are hoping that the city will have inscriptions to tell us dates about rulers and things.
What can you tell us about who the people who built these ruins were? When were they there, and where did they go?
The earliest dates on some of the sites are about 2000 BC, but that has to do with some of the structures. So there were people in Mesoamerica from about 10,000, but the people we call Maya were actually different groups with related languages. But we say Maya because at the time of the period in which some of the biggest cities were built, they did share, the rulers at least shared a language in the way they shared Latin in Europe. And so that's the language that the inscriptions are written in. Then at about 800, 900 AD, the dynasties had a collapse and the whole landscape changed. People spread out and you developed a lot of small cities. So when the Spaniards came, the landscape was covered with smaller sized cities, smaller populations. They weren't centered in these large cities, which is evidenced by the site like Valeriana.
Presumably then, this now opens the door to pointing us towards a rich archaeological seam, which hopefully no one has been to previously, and we have a chance to see some of this stuff in an undisturbed state.
There are many sites that have not been excavated. This is a newly discovered one, but there still are many that remain as ruined temples in the forest.
And what questions do you hope we'll be able to get a bit closer to the answers to with archaeological finds like this?
I've been interested in Maya cities for some time, Maya urbanism, and I think with the results from this survey, and not just the temple, but the rest of the settlement, that we'll get a better handle on how these cities functioned. Because the Maya didn't have cattle or sheep or goats, so they didn't have pasture, they didn't have that sort of domestication. So it can tell us something more about how the cities were structured and the population, of course. And then, as I said, there should be monuments with inscriptions that will give us dates and hopefully some more information on the kind of integration that was developed by the Maya rulers.
I reckon that's the plot for the next Indiana Jones movie, actually. That was Elizabeth Graham at UCL. Sometime around 375 million years ago, fish made the bold move out of the water and onto land. And although we have a rough idea as to the morphology of the first few species that made this leap, including the famous fish Tiktaalik, the precise structures of their feet-like fins have been lost to time. Fossils, for all they can reveal about our past, tend not to preserve soft tissues like muscles and tendons at all well, and those are, of course, how we would tell how our ancestors first walked. But now, a bit of 21st century technology is being touted as a way of determining what those early steps might, or critically might not, have looked like millions of years ago. It's a robotic fish. And Will Tingle took a trip down to Cambridge University's bio-inspired robotics lab to see Michael Ishida and hear how robots can provide the answers to some of life's earliest mysteries.
It sounds a little ridiculous sometimes when I say it out loud, but obviously with a fossil, you can't observe it moving around. It's just a static piece on display. And so paleontologists have all this expertise in kind of putting together these pieces, making strong inferences about how it may have moved, how things might have fit together. But there's no real way to loop that back and kind of prove this is for sure how things happened.
What's missing from current fossils that you need in order to get that data?
There's a lot of things missing. We're very lucky to get partial fossils. And as I'm sure you know, there's many species that we think existed that we just haven't found fossils of yet. Not only are these fossils we do have incomplete, but we're probably missing some in this evolutionary chain. And so with robotics, we can design a new robot that kind of fits into the gaps. And so all of these ways of building something to give us more information, more data, is something that we're very interested in.
So how do you go about doing that? How do you go from fossil of what you think is a fish to a robot in front of us right now that can move and can provide some insight?
Obviously, there's no actual model that replicates the exact animal. You can't build a robot that replicates every muscle, every tendon, every piece of soft material. So the first job is to kind of simplify and say, what is the research question we're actually asking? Is it about the fin? So then maybe if our research question is about how this fin of the fish is able to support its body weight, maybe then we build a very detailed fin with the exact bones and the soft material we think it had, and then we can take more simplifications with the rest of the body. We can put the motor on the middle of the body so that it doesn't affect how this fin moves, because the fin is what's most important. We have a long history of what's called bio-inspired robotics. That's just robots inspired by animals that we can see today. And so there are some species of fish today that are able to swim and walk. So there's things like Polypterus, which is native to Africa, that kind of lives in a swampy area. It can swim in the water and kind of move from puddle to puddle. You have mud skippers that are native to places like Japan, that I'm sure you've seen all the BBC videos of the thing kind of scooting across the sand. But the point is there's many species today that we can look at and get a first kind of understanding about how a fish might be able to walk. the physics of fish haven't really changed from now to 500 million years ago. If you understand something about walking fish today, you can then kind of apply that knowledge to ancient walking fish. Understanding as many species as we can today will give us some insight into this ancient animal. And we can see, oh, this strategy for walking on land in sand, let's apply it to this robot fish fossil. Oh, maybe it doesn't work very well in sand. Okay, how about in mud? Oh, maybe this also doesn't work very well. Well, maybe rock. Oh, okay, maybe this is kind of more of the environment we're thinking of.
So it's almost as important to understand the environment that they lived in hundreds of millions of years ago as it is to understand their physiology as well.
Exactly. So all of evolution is driven by the environment, whether the environment is water, whether it's additional oxygen in the air, whether it's different predators that live in your environment. Everything in evolution is kind of driven by this interaction with your surroundings and the population around you. Building a robot also helps us understand the environment very simply, right? Instead of building a computer model where you're simulating the water around it and the mud at the bottom and, we can just build a robot, put it into a water environment or a muddy environment, and then we don't have to make this additional guarantee that our simulated mud is accurate.
This is a very promising and burgeoning field. Should this come good and you work out how Tiktaalik and its friends all got out of water, 400 million years ago, where would you like to go next?
That's a great question. I think the power of robotics really is to help us explore what we call counterfactuals, things that didn't happen. We can see the fossil record is filled with animals that did exist, they did happen. And so using a robot to try other morphologies or other sizes or other designs that nature did not come up with or that we haven't observed is something that we're really interested in. Because then we can see, oh, why did nature not come up with this idea? Why did the certain species die out faster than another species? We think there's a great untapped potential in paleo-inspired robotics. We have so many questions about the ancient history of our world that we can only get a partial, tiny picture of through fossils and things that are preserved today. So collaboration between roboticists, paleontologists, and biologists is going to be super important to understand these ancient creatures.
Michael Ishida, and that paper just came out in Science Robotics. He was speaking to Will Tingle. Well, now let's stick with the evolutionary past, because in this question of the week, James Titko has been taking on this prehistoric counterfactual from listener Colin.
If the extinction level event that wiped out the dinosaurs didn't happen and dinosaurs continue to roam the earth, would mankind still have risen to be the dominant species on the planet?
Thanks, Colin. How might man have fared in a world where T-Rexes roamed? In a bid to answer your question, I've enlisted the help of Charlotte Kenchington from the Department of Earth Sciences at the University of Cambridge.
Now, that is an excellent question. There are so many factors that play into whether or not a species or a group of species will become or even remain dominant. Evolution is a complex dance between biological processes like competition and non-biological ones like climate change, let alone extraordinary events like major volcanic eruptions or meteorite impacts. When we think of groups like the dinosaurs, we also need to think of them in all their diverse glory. There were little unimpressive beasts as well as the iconic giants of popular culture, and in fact there are plenty of dinosaurs alive today. In your garden, on your bird feeder, in your local pond. But of course, usually when we talk about dinosaurs, we're referring to the big scaly beasts, the non-avian dinosaurs, rather than our feathered friends.
So why might the larger species have declined? Here's Charlotte again.
Non-avian dinosaurs were actually already on the decline before the mass extinction event that wiped them out. The exact reasons are still a question of ongoing debate, but the Earth's cooling climate would have made it much more difficult for larger creatures, with their enormous dietary needs, to thrive. Now after that, there was a dramatic temperature rise around 20 million years ago that saw the evolution of huge land mammals like the giant sloth and of the enormous terrorbirds, the true heirs to the T-Rex crown, if you will. Now, the earliest hominins, which are the ape-like group, are from around a similar time, around 7 million years ago. And once apes, with their complex brains, capacity for tool use, wide-ranging diet and remarkable stamina appeared, the rise of a dominant hominin species feels almost inevitable.
The great big what if then? Would our ancestors have become the dominant species had dinosaurs not become extinct?
Ultimately, the big non-avian dinosaurs were already on their way out. The meteorite and volcanic activity just finished them off, kind of sped up the process of their demise. But that said, Without all the other climatic shifts and evolutionary trajectories that followed, there is no saying that apes, and therefore humans, would have evolved at all, let alone risen to our present-day dominance.
It's hard to look back on the story of life and draw many conclusions about how it could have panned out differently because of one simple fact. It didn't. Thanks for the great question in any case, Colin, and to Charlotte Kenchington from the Department of Earth Sciences at the University of Cambridge for helping us answer it. Next time, we're answering this question from another listener.
Hello, Naked Scientists. Van in Nevada here. A friend is encouraging me to take a cancer screening test that scans for many different cancers. A review of one test says, while overall it picks up 90% of stage 4 cancers, it only detects an average of 17% of stage 1 cancers. Yet it is being touted as a test that can detect cancer early. Are these tests worthwhile? Thank you.
A very important one that we will be sure to get to the bottom of for you. And if you have an answer for us, or of course a question that you'd like us to delve into, please do get in touch. It's chris@thenakedscientist.com. You can also follow the discussion on our website at nakedscientist.com/forum. Next time, we're wondering, should we ban smartphones in schools? The Naked Scientist comes to you from the University of Cambridge's Institute of Continuing Education. It is supported by Rolls-Royce. I'm Chris Smith. Thanks for listening. And until next time, goodbye.